Welcome to the Antonio Zamora podcast that discusses a variety of scientific topics. Ice impacts on viscous and solid targets. The story of the Carolina Bays. This video discusses the mathematical model for calculating the size of the Younger Dryas comet and analyzes impacts of ice on various targets. One of my recent videos calculated the diameter of the Younger Dryas comet applying the law of conservation of energy by using estimates of the energy of the secondary glacier ice impacts that made the Carolina Bays and the Nebraska rainwater basins. The size of the comet was surprisingly large. The diameter was about 8 kilometers for a comet with a density of rock and 12 kilometers for a comet with a density of water. It is assumed that the Carolina Bays were made by secondary impacts of glacier ice ejected by a comet impact on the Laurentide ice sheet. The mathematical model uses the Bay geometry to calculate the launch angles. Ballistic equations provide the projectile speed. Yield equations correlate the size of the Carolina Bays to the energy of the ice projectiles. The energy of the extraterrestrial impact corresponds to the combined energy to create the Carolina Bays. The program to calculate projectile size from crater diameter was developed by Professor J. Meloche and Ross Baer. The yield equations relating energy to crater size were developed from experiments of nuclear explosions, conventional military explosives, and dynamite explosions for mining, road building, and other civilian uses. The program requires the crater diameter, the impact velocity, the angle of impact, and information about the physical characteristics of the projectile and the target material. I tried to verify the results of the projectile size calculator by drawing ellipses representing Carolina Bays and the calculated projectiles at a 1 to 1000 scale and comparing the images against the experimental results. I concluded that the results based on this calculator were reasonable. I mentioned that the Carolina Bay, with a length of 1,613 meters, was created by an impact of 44.3 megatons, and that this energy was comparable to the most powerful hydrogen bomb ever tested by the Soviet Union, which was the Tsar Bomba with a yield of 50 megatons. I have previously calculated very energetic impacts for large bays. The inset shows the Carolina Bay with a calculated energy of formation of 116 megatons. This is more than double the yield of the Tsar Bomba. This image has Carolina Bays that are even bigger and would have been formed by impacts of huge chunks of glacier ice. It is evident that no animals could have survived the saturation bombardment by the ice chunks that created these Carolina Bays. My video got a Twitter response from Dr. Martin Sweatman that said, "The energies you are finding, Tsar Bombish, would create craters in hard ground too. Do we see any? If not, it suggests the Carolina Bays are just erosional features or your energy model is wrong." I respect Dr. Sweatman's opinion a lot. Dr. Martin Sweatman is a fellow of the Royal Society of Chemistry in the School of Engineering at the University of Edinburgh. He is the author of Prehistory Decoded, a science odyssey unifying astronomy, geochemistry, and archaeology. Dr. Sweatman has a YouTube series that carefully evaluates the peer-reviewed literature about the Younger Dryas impact hypothesis, which is archived in the Cosmic Tusk website. There is a link in the description below to Dr. Sweatman's book. I replied to Dr. Sweatman, "Ice is fragile and disintegrates when colliding with rocky ground. There is evidence of landslides at the Younger Dryas boundary that could be the result of such impacts." Then I added, "The geometry of the Carolina Bays is perfectly elliptical. How can erosion do that?" I wanted to emphasize this point because the elliptical geomorphology of the Carolina Bays and the radial alignment toward the convergence point in the Great Lakes implies that they originated as inclined conical cavities from secondary impacts. As Dr. Sweatman suggests, there must have been secondary glacier ice impacts on hard ground also. Such impacts had enough energy to cause landslides on unstable ground. Some of the largest known landslides in North America are found in Montgomery and Craig counties, Virginia, in the Blacksburg, Wythe Ranger districts of the Jefferson National Forest. One of the landslides is more than 3 miles long. The ancient giant landslides extend for more than 20 miles along the eastern slope of Sinking Creek Mountain. Evidence suggests that the landslide movement occurred between about 10,000 and 25,000 years ago during the Pleistocene epoch, which is within the time frame of the extraterrestrial impact. Another clue of the glacier ice bombardment on hard ground may be the boulder field at Hickory Run State Park in Pennsylvania. The current geological explanation for this field is that the boulders are generated from the fracturing of an upslope bedrock outcrop by alternating freezing and thawing. As boulders accumulate at the base of the rock slope, periglacial ice-catalyzed heaving and sliding transports them downslope during cold climatic periods to form boulder fields. There is evidence that this area was covered by an ice sheet at least once. However, the moraines left by retreating glaciers are not neatly level fields like this one. Acoustic fluidization may explain the level field of rocks. A mass of dry rock debris is fluidized by the fluctuating pressures induced by strong vibrations or acoustic waves traversing the terrain, according to Melosh 1979. Large rocks, which are normally pushed tightly against each other by the pressure of overlying rock debris, suddenly become free to slip during a transient low-pressure fluctuation. Strong vibrations from the shock of an impact can briefly fluidize rocky debris and cause it to flow like a liquid. A barrage of secondary impacts of glacier ice had enough energy to produce seismic vibrations capable of acoustically fluidizing this boulder bed to give it its level characteristic. The ice boulders that hit solid ground disintegrated explosively with energies equivalent to 13 kilotons to 3 megatons of TNT. That energy is equivalent to earthquakes of magnitude 6.0 to 7.54. Here is another example of a landslide that has been dated to the time of the extraterrestrial impact. Jacobson et al. Described a landslide in Pendleton County in West Virginia at 12,920 years before the present that corresponds to the time of the Younger Dryas onset. These landslides are circumstantial evidence of the extraterrestrial impact, but it is the type of effect that would be expected from a hailstorm of massive ice boulders. I replied to the Twitter conversation. Ice has 1/3 the density of rock and very low tensile strength. I meant to say yield strength. A big impact at ballistic speed on rock would make a dent and scatter ice shards laterally at great speed. This is what happens with hailstones. Dr. Sweatman replied, "True, the impact velocity is very important. With air resistance, impact velocities of maybe just a few thousands of meters per second are expected. What happens for ice on rock with impact angle 35 degrees at this velocity? I don't know, but if you could provide evidence other than hailstones." I often get suggestions about scaling up experiments beyond hailstones and ice cubes. I think that it would be very instructive to shoot an ice ball with a diameter of 27 meters at 3,000 meters per second somewhere in the East Coast. The impact would have energy of 11 kilotons and it would make a Carolina Bay 135 meters long. However, there could be a lot of casualties and people would complain about sonic booms and tremors, so it is safer if we just keep using numerical models. Dr. Sweatman continued, "But you're talking about impacts with huge energies, 50 megatons. How can that much energy not create a crater on hard ground? Barringer meteor crater is estimated at 10 megatons. Don't care what the projectile is made of, something is wrong." Another tweet said, "I like your secondary impact scenario, but using an energy model for cratering when you have very different mechanism is likely throwing your energy estimates off." These tweets motivated me to conduct additional experiments with ice projectiles to compare the impact mechanisms on viscous and solid targets. Before describing the new experiments, it is useful to review the mechanism of hypervelocity impact cratering. The first stage begins when the projectile contacts the target surface. The swiftly moving projectile pushes target material out of its path, compressing it and accelerating it to a large fraction of the impact velocity. At the same time, the target's resistance to penetration decelerates the projectile. The shock pressures reach hundreds of gigapascals and exceed the yield strength of both the projectile and target. The projectile and the target melt or vaporize during the great explosion that results from the release of such pressures. The excavation stage begins immediately after the contact and compression stage. A hemispherical shock wave propagates through the target, creating a hemispherical crater shortly after the impact. The crater diameter initially expands by horizontal compressive forces at a fraction of the impact velocity, but the rate of growth in depth slows and finally ceases before its radial growth stops. During the excavation phase, material is ejected in the form of an expanding conical ejecta curtain. The innermost ejecta are launched first and travel fastest in parabolic trajectories. Ejecta originating further from the center are launched later and move more slowly, falling nearer the rim. This image illustrates how large, heavier material falls closer to the impact point and small, lighter material falls further away. The growing transient crater is lined with broken and molten rocks that flow upward and out of the crater along the crater walls. The modification phase starts after the crater has reached its widest diameter and material starts falling back into the crater. The bottom of the crater accumulates a pool of broken and molten rocks. In contrast to the impact of projectiles on hard ground, the transit of a projectile at ballistic speed through a viscous medium does not create great pressures and material transitions that characterize extraterrestrial impacts. Passage of a projectile through a viscous medium produces heat and displaces material, which dissipates the kinetic energy of the projectile and slows it down. The projectile will stay intact and create a conical shockwave as long as the frictional forces do not exceed the yield strength of the projectile. A bullet traveling through the air creates a conical shockwave that disappears almost instantly. A tennis ball dropped in water also creates a conical cavity and displaces an ejector curtain. The conical cavity collapses when water rushes to fill the crater and initiates an oscillation that produces expanding circular ripples from the point of impact. The passage of a bullet through ballistic gel also creates a conical cavity, but unlike the cavity in water that collapses under the force of gravity, the elastic nature of the ballistic gel closes the cavity but retains the tubular trail indicating the passage of the bullet. Finally, a bullet striking a viscous, non-elastic medium like modeling clay creates a conical cavity that retains its shape for a long time. These cavities are modified by gravity at a rate dependent on the flow characteristics of the medium. This is the impact of an ice projectile fired from a slingshot toward the concrete floor. The contact and compression phase of the impact of an ice projectile on a concrete surface shows that the projectile disintegrates into many fast-moving ice shards. The impact does not even create a dent on the hard surface. Erland Schulson, who is a professor of engineering at Dartmouth College, explains that the brittle failure of ice under compression is marked by sudden material collapse after shortening less than about 0.5%. The failure mode is generally shear faulting on planes inclined at about 30 degrees to the direction of maximum principal stress. Here is another example of an ice projectile impacting a concrete target. This experiment shows that a large portion of the ice projectile disintegrates when it hits the hard surface, and some big pieces are scattered from the point of impact. Every impact is different, but they all have common characteristics. The glacier ice boulders impacting solid ground could not liquefy the ground to form Carolina bays, but they fragmented into high-energy ice shards that were lethal to the megafauna. The Orleton Farms mastodon, which was found in Ohio, may have been a victim of such a barrage. One of the ribs lay beneath one of the tusks, while another was thrust to an aperture in the pelvis. A shoulder blade rested to the right of the skull, and one of the large neck vertebrae was found about 10 feet from the skull, near a portion of the pelvis. Yet, the bones of one of the feet remained intact and in place, very possibly in the spot where the animal last stepped. Now we compare the impact of a similar ice projectile on a viscous target consisting of equal parts of sand and clay. Even though the ice projectile hits the viscous target with the same energy as the hard target, the viscous medium is displaced and allows the projectile to travel through the medium to create a conical impact cavity. Unlike an impact on a hard target, the contact and compression phase and the excavation phase are not distinguishable because the yield strength of the projectile is never exceeded. The movement of the projectile through the medium is what creates a cavity, rather than the explosion of a projectile that unloads from high pressure. Debris is ejected in ballistic trajectories from the point of impact. Pay attention to the depth of the ice projectile. In this image, the projectile is not as deeply embedded into the target surface as in the previous image. This is due to an elastic rebound effect in spite of the high viscosity of the target. At this point, the projectile has reached its final resting place, but the excavation is still going on as additional material is ejected in ballistic trajectories. It is important to note that a circular seismic wave is generated from the point of impact. During the bombardment of glacier ice that created the Carolina bays, these seismic waves liquefied the ground and made possible the formation of conical impact cavities. I will now replay the video. Look carefully for the circular shock wave that radiates from the impact point in the slow motion part of the video. Thus far, we have seen impacts on concrete, which is as hard as stone, and impacts on a viscous target. Now we're going to see an impact on terra firma, or solid earth. This image shows the target that I used to simulate the small clustered Carolina bays in New Jersey, but it is now dry. There is just a cloud of dust and a bounce. Unlike the impact on the concrete target which remained unaffected by the projectile, an impact on solid earth produces a dust cloud from the target's surface. The target deforms enough to absorb some of the energy and prevents the ice projectile from exceeding its yield strength. The result is that the ice undergoes minor fragmentation and ejects a cloud of dust. Then, a large piece of the projectile bounces off. This bouncing behavior would not be expected for large ice projectiles. The experiment suggests that glacier ice boulders that impacted solid ground at ballistic speeds would not have left big craters, and this explains why we only find Carolina bays on ground that was subject to liquefaction. Oblique impacts create inclined conical cavities, which when viewed from above have elliptical geometry. This makes sense because ellipses are conic sections. Notice that the projectile stops toward the leading edge of the ellipse and the overturned flanges become raised rims around the cavity. Vibrations from adjacent impacts promote viscous relaxation that reduces the depth of the inclined conical cavities to create shallow elliptical bays. This image shows the transformation of adjacent conical impact craters into overlapping bays through viscous relaxation. The image on the lower right shows Carolina bays with different types of overlaps. The proponents of the Aeolian and lacustrine hypothesis have never attempted an experiment to create overlapping bays. A viscous target slows down an ice projectile without exceeding its yield strength. This allows the ice projectile to penetrate the medium and form a conical cavity that becomes a shallow bay through viscous relaxation. These experiments have not answered the question of whether the numerical models provide accurate answers, but they have shown that glacier ice impacts on hard ground could have fragmented the ice boulders without leaving any long-lasting traces on the target surface. An ice boulder with 50 megatons of energy at ballistic speed would probably fragment when impacting hard ground without creating big craters because ice is very fragile and it just crumbles upon hitting a hard surface. In a few centuries, normal erosive processes and vegetation would conceal any traces of the ice impacts on solid ground. The Carolina bays that formed on unconsolidated soil may be the only evidence left of the glacier ice bombardment. Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.